Welcome back to AP Chemistry. My name is Mr. Krug, and today we're going to be looking at some of the main types of intermolecular forces. In this video, we're actually going to be focusing on two of the main types of intermolecular forces. Now, before we do that, we need to talk about what are these forces. Well, intermolecular forces specifically are talking about forces that make molecules stick together, whereas intramolecular forces are the forces that hold a molecule or an ionic compound together. So specifically, we're talking about covalent and ionic bonds when we say intramolecular forces. Now, normally, intermolecular forces are going to affect physical properties of a compound. When we talk about boiling point or melting point or other things like that, normally intramolecular forces like the bonding within the molecule will affect how reactive or how unreactive a molecule is. Now, usually intermolecular forces are weaker than covalent and ionic bonds. We know that because, for example, we can take a droplet of water, and you've probably seen something like that before, and we can take a knife or some other object and split that in two. And we're basically breaking some of the intermolecular forces apart. On the other hand, you really can't do that to intramolecular forces with covalent or ionic bonds. For example, if you take the same water droplet, you can't take a knife or something and split the hydrogen and oxygen atoms apart. You need something a little stronger than that. Well, let's take a look at the first type of intermolecular force, and that will be what are called London dispersion forces. Now, this is a term that's sometimes abbreviated as London forces. Sometimes it's abbreviated as dispersion forces. In this presentation, we sometimes just abbreviate it as LDF to make things a little bit shorter. Well, let's start by visualizing what an atom of neon looks like. Now, of course, this is a fairly simplified picture. We have 10 protons in the middle, and there are 10 electrons that are buzzing around that nucleus in the electron cloud. Now, generally speaking, we're going to assume that all of these 10 electrons are pretty much evenly distributed throughout that atom. Now, that's pretty typical in an atom or a compound. The electrons are fairly evenly distributed as you look around the molecule or the atom. But something we also know is that electrons are always moving. In fact, the Heisenberg uncertainty principle tells us that we never know for sure exactly where the electrons are going to be. And so it's possible that at some moment in time, the electrons are going to look something like this. And in this particular atom of neon, it's actually the same atom, but just because of chance, the electrons happen to be all on this side of the atom. And so this is kind of a lopsided distribution. As a result, when you have all these electrons on this side of the atom, it's going to give this side of the atom a partial negative charge. So I'm going to kind of show that with this lowercase delta and then a negative sign to show that that part of the atom has a partial negative charge. Now, if that's negative, that means the other side over here has a partial positive charge. So now we have an atom that has kind of a pole to it, and this is called an instantaneous dipole. And this is what happens when you have this very temporary lopsided distribution of electrons in an atom or a molecule. Now, because of this, if we take a look at what this can do to other nearby atoms, if this atom here on the right is our original structure with that negative instantaneous dipole over here and a positive one on this side, well, that can actually affect nearby atoms. And so if we have a neighboring neon atom like we have over here on the left, well, the electrons, this negative side, is going to push those other electrons over. And so, you know what? We're going to have a partial positive over here and a partial negative on the neighboring atom. And so since we have a partial positive here and a partial negative on that atom, we actually have a little attraction in between those two atoms now. And it's not a very strong attraction, but that's what a London dispersion force is. It's when we have these instantaneous dipoles that kind of cause somewhat of a cascading effect and actually cause an intermolecular force between those two atoms. And so, as it turns out, every atom, every molecule can do this. All molecules exhibit London dispersion forces. It doesn't matter if it's ionic or covalent or polar or nonpolar. Every single molecule will exhibit these LDFs. Now, there are some molecules, in fact, most molecules, as it turns out, can exhibit other forces. We'll talk about the polar molecules and what they can do here shortly. But right now, we know that nonpolar molecules have only London dispersion forces. Now, if you need a little review of that, you might want to go back to a previous video. Nonpolar molecules would be atoms, or would rather be molecules such as, for example, carbon tetrachloride. You might remember when we drew Lewis structures earlier in this course, we had these, that they're fairly evenly distributed, and in a molecule of carbon tetrachloride, the electrons are evenly distributed. There is no region of unbalanced negative charge. So that CCl4 would be a nonpolar molecule. It would have only London dispersion forces. Now, on the other hand, if we had a molecule like this, NH3, ammonia, we might remember it has somewhat of a pyramidal structure because it has an unshared pair of electrons right there. And because it has this unbalanced region of negative charge, that's a polar molecule. So, nonpolar versus polar. So that's just a quick review of that. Well, if it's nonpolar, it has only London dispersion forces. Now, here's another important thing about London dispersion forces. The more electrons a molecule has, we say the more polarizable it is. And as a result, it's going to have stronger LDFs. And so in our previous example, we had neon, which has 10 electrons. Well, if we imagine, let's say an atom of helium, helium would only have 2 electrons. So if we can imagine those 2 electrons over here hanging out, and if they're both on the same side, well, there's a London dispersion force there, but these 2 measly electrons really can't do a whole lot. The force is so weak, it's almost practically negligible. So the more electrons something has, it's going to have stronger London dispersion forces. So helium would be very weak. Neon is greater. Something like radon would have 86 electrons. So imagine all those on that lopsided structure like that. That could be a fairly strong force as far as those go. Now, normally speaking, the stronger that the molecule's intermolecular forces are, we're going to say its boiling point and also its melting point is going to be higher. And so in the case of neon, it would have more electrons than helium, so it's got a higher boiling point than helium would. Now, this is an important point also that oftentimes pops up on the AP exam. Generally speaking, London dispersion forces are the weakest of all the intermolecular forces. However, there are some molecules that have so many electrons, and as a result they're so polarizable, that's an important word, polarizability, their intermolecular forces end up being stronger than some polar molecules. Now, let me give you an example of that. If we think of a tire that's on the road, that is made of rubber. And the molecules in that rubber polymer are so large that we can say that its intermolecular forces are much stronger than some polar molecules. And we want it to be that way because you don't want your tire to start melting on you as you're driving down the road. You want the forces here to be very, very strong. So, well, the very high molecular mass of these rubber polymer molecules allow them to be that way. So the more electrons you have, the more polarizable the molecule is, and you have stronger intermolecular forces. And so sometimes on the AP exam, you'll have a couple examples where they show you something that's polar and something that's nonpolar, and it turns out that the nonpolar one has a higher a boiling point. And, well, that's because its London dispersion forces are just so strong, it's very, very polarizable. Well, let's take a look at a couple of examples. So the first question, which of these molecules exhibits London dispersion forces? Well, if you recall back to the notes earlier, we said that every molecule has LDF forces, so it would be both of them. So all molecules, all compounds, all atoms have London dispersion forces. Well, let's take this a step further. Which of these two molecules has stronger London dispersion forces? Well, it would be the one that has more electrons and thus is more polarizable. So that would be the C4H10, this molecule of butane. Now, as a result, which one has the higher boiling point? Well, once again, it's the molecule that has the greater intermolecular force, which would be the butane molecule. Let's check our work here, and we can actually look up the boiling points, and sure enough, the boiling point of butane is well over 200 degrees higher than it is for methane, just because it's more polarizable, more electrons. How about this question? Rank these nonpolar molecules in order of increasing boiling point. Well, we know that when it comes to molecules with only London dispersion forces, it all comes down to how polarizable they are, how many electrons they have. Well, helium is the least. It has only 2 electrons, so helium would be the lowest. Argon has more electrons. It has 18 electrons, so it would be the next. And C3H8 propane would have the highest boiling point because it has the highest number of electrons. It has about, if I counted this up right, about 26 electrons. So the propane would actually be the highest. So let's see if we got it right. Here are the boiling points, and sure enough, helium is the lowest, very, very close to absolute zero. Argon is next, negative 186 degrees Celsius, and propane is actually the highest over here at negative 42 degrees. Let's take a look at another type of intermolecular force, and these would be dipole-dipole forces. This time, let's think about a molecule of HCl. So hydrogen chloride gas, and here we have a molecule of that. And we might remember that from an earlier lecture that chlorine is a very electronegative atom. And so if we draw the Lewis structure for this, perhaps it's a little bit easier to see. And so we have these lone pairs, these unshared pairs of electrons that are surrounding chlorine. Hydrogen doesn't have those. And so as a result, there is a pole here in this molecule. There's a negative charge on that chlorine side of the molecule and a partial positive charge on the hydrogen side of that. And so it is a polar molecule, so it's kind of lopsided as far as electron distribution goes. Now, as it turns out, that molecule is going to have an effect on its neighbors. And so if we look at, say, some more molecules of hydrogen chloride, and we think about the partial charges on those molecules, well, you know what? The negative side of this molecule has an attraction to the positive side of that molecule. So there is a little attraction there. And as it turns out, that's what we call a dipole-dipole force. And we have one over here too. There's this positive side attracting the negative side of a neighbor. And so, you know what? There we have a dipole-dipole force as well. And so those are some forces that can hold these molecules together. It's an intermolecular force. Now, only polar molecules exhibit dipole-dipole forces. And so we talked about ammonia is a molecule that is polar. We can talk about HCl. We'll talk about some special forces that NH3 has in a future video. Other polar molecules, I think we could throw in NF3, a few others as well, nitrogen trifluoride. Now, don't forget that when something has dipole-dipole forces, it doesn't mean that it doesn't have the LDF as well. All molecules have London dispersion forces. And so if it's polar, it's going to have both dipole-dipole and London dispersion forces as well. Usually, those dipole-dipole forces are stronger than the LDFs. Usually, given the similar numbers of electrons, you'll find that the polar molecule is going to have the higher boiling point than the nonpolar molecule. So let's take a look at an example here. Which of these molecules has the higher boiling point? Well, we know that NCl3, nitrogen trichloride, is a polar molecule. If we take a little space here and try to draw the rough structure of that, I'm going to leave out some of the unshared pairs on the Cl, but this is the basic, this is the basic structure of that molecule. And so we know that because it has this lone pair on the central atom, it's not canceled out by anything else. It's an unbalanced region of negative charge. That is a polar molecule. And so NCl3 is going to have dipole-dipole. It's also going to have LDF. On the other hand, the butane molecule here, C4H10, just has a long chain of carbons and hydrogens. Generally speaking, hydrocarbons with just carbons and hydrogens in them will be nonpolar. And so this has only dispersion forces. And so since nitrogen trichloride has the dipole-dipole forces, we can say that it has the higher boiling point of these two. Now let's check that. And sure enough, nitrogen trichloride, because it has a dipole-dipole force, in addition to its LDF, its boiling point is over 70 degrees higher than this molecule that has only London dispersion forces, which is butane. Now, that brings us to the end of this discussion. In our next video, we're going to talk about hydrogen bonding and another type of force as well. So hopefully at this point, you're able to differentiate between London dispersion forces and dipole-dipole forces. Hopefully you're also able to decide which molecules have London dispersion forces and which ones have dipole-dipole forces. And you can also compare boiling points and melting points for these molecules. If you learned something, I hope you'll subscribe to my channel. Give the video a thumbs up if you learned something, and hope you subscribe for more AP Chemistry videos.